Okay, today we're grabbing a stack of sources that, well, they propose a genuine revolution in physics. We're diving deep into the Graviton Pressure Theory, GPT.
That's right.
Specifically, Part 9 of this framework. It takes a cold, hard look at existing observational data and basically claims our understanding of gravity, time, cosmology.
Yeah.
It's fundamentally wrong.
It's a huge claim. I mean, unprecedented, really. And it's built on this massive theoretical foundation. GPT isn't just tweaking things.
No.
It aims to completely dismantle 3 pillars of modern cosmology. It wants to get rid of dark matter, says we don't need cosmic inflation, and replaces space-time curvature.
The whole geometric idea?
Yeah, replaces it with pure field dynamics,
So-
pressure, basically.
So the sources define the universe not by geometry or, invisible stuff, but by this structured pressure-bearing graviton field. Our mission today is to unpack how GPT claims to pull this off.
Right.
It promises to substitute mystery with mechanism. That's the phrase they use. Rooting physics in observable causal coherence.
Exactly. And we're looking at 6 key observations, big ones. Stuff like how galaxies move, right down to how your GPS works.
Your phone, yeah.
And the core argument, the thread running through all of this, is that effects we currently explain with attraction or curvature, well, GPT says they're actually just about pressure gradients and structure, coherence within this universal graviton field.
Okay, let's start with maybe the biggest cosmic mystery, the main reason we invented something we literally can't find, dark matter.
Right. The observation's solid. Stars way out at the edge of galaxies, they just don't slow down like Newton says they should.
You expect velocity to drop off the further out you go, the Keplerian decline?
But you don't see it. You see these flat rotation years. Stars keep whipping around fast.
Which led us to needing something else, something massive and invisible, dark matter, to provide the extra gravity.
It works in the models. It's a successful patch, you could say. But yeah, the substance itself, still elusive.
So GPT comes along and says, look, the observation is fine, the interpretation is wrong. These flat curves aren't evidence of missing mass.
But of structured pressure.
How does a pressure field do that? Keep a whole galaxy spinning uniformly?
Okay, so the theory posits that big things like galaxies, they don't just pull stuff gravitationally. They actively organize the background graviton field around them into layers, structured layers.
Coloring onion layers.
Sort of, yeah. These layered pressure gradients form what GPT calls quantized corridors of stable motion.
Quantized corridors.
So motion inside the galaxy is guided by structured compression and resonance, meaning the field itself, the structure of it, maintains the stability, almost like a gyroscope maintaining its orientation.
Ah, okay, so it's intrinsic stability, not an external pull. If I'm a star in one of these corridors, I'm not being yanked towards the center.
Exactly. You're being sort of constrained, held in tension by the organized field itself. And this is where the argument about simplicity, about parsimony, comes in really strong. The sources point to the sparse data analysis.
Spitzer photometry and accurate rotation curves. Huge catalog.
Yeah. And standard dark matter models, they need unique settings for pretty much every galaxy. Complex dark matter halo profiles, different parameters adjusted case by case. Lots of free parameters.
Okay, so how does GPT compare? What does it need?
Well, GPT claims it can reproduce these flat curves for all sorts of galaxies. You know, the classic spiral NGC 3198, the little dwarf M33, even the giant UGC 2885.
Diverse systems.
Very diverse. And it does this by applying universal field principles, just 2 main parameters. P0, the baseline pressure of the universe.
Like a background hum.
Kind of, yeah.
Yeah.
And K, the field attenuation constant. GPT proposes these are fundamental constants, like the speed of light. They govern the field structure for all galaxies. They aren't tweaked for each one.
That's a critical difference, isn't it? Dark matter needs custom tailoring for each galaxy.
While GPT claims to use a universal blueprint.
So the flat rotation curve becomes evidence of the field maintaining coherent tension equilibrium. And if that's true, poof, dark matter just isn't needed.
It becomes redundant.
Yeah.
It's a massive shift, philosophically, too.
Definitely. It moves the reason for stability from mass pulling things to the structure of the field itself.
Yeah.
Replaces an unseen thing with an intrinsic mechanism.
Exactly.
Okay, let's shift scales. From galaxy-wide stability to dynamics. Gravitational waves. LIGO's detection. GW15091 first. Huge win for general relativity, right? Ripples in space-time itself.
That's the GR view. GPT sees the same signal, same data, but but interprets it differently.
Oh,
It says those signals aren't geometric distortions. Remember, in GPT, mass doesn't warp geometry, it compresses the graviton lattice.
right.
So a really violent event like two black holes merging causes a massive coherence rupture and realignment within this lattice structure.
A tear in the fabric.
More like a shock wave through it. The wave propagates out as a pressure phase ripple. It's a disturbance in the medium, not a warping of the medium.
Okay, I'm trying to get my head around that. In GR, the strain H is a fractional change in length, right? Space-time stretching and squeezing. If you throw out space-time warping, what is LIGO actually measuring then? What is H?
It's measuring a pressure difference directly. The sources define it as HGPT equals delta PG over 0.
So the pressure fluctuation relative to that baseline pressure we talked about.
Exactly. It's a fractional pressure change. Think of it like a stress measurement in a material, not a geometric change in distance.
Okay, that's different.
Yeah.
And it must lead to different predictions, especially about how the waves travel and fade, right? Attenuation.
Absolutely. GR predicts these waves spread out uniformly, and their strength should drop off smoothly with distance following that simple inverse square law, the one factor.
Makes sense for geometry.
But GPT says the wave is traveling through a physical medium, the graviton lattice. So it predicts the attenuation will be affected by the local density of that medium, the local pressure.
So if the wave goes through a region where the field is really dense, really compressed, it would dampen differently.
Precisely. GPT predicts an exponential damping, e to the minus alpha r. And crucially, that damping coefficient alpha wouldn't be constant. It would vary depending on the field structure the wave passes through.
That's a subtle but potentially testable difference. If we saw a gravitational wave fade out exponentially or unevenly over vast distances,
That would be very hard for the pure geometric ripple model of GR to explain. It would strongly favor a medium-based theory like GPT.
okay, that brings us neatly down to Earth, or rather just above it, GPS timing.
Our everyday reliance on GR, basically.
We know those satellite clocks run faster than clocks on the ground, by about 38 microseconds a day, and we constantly correct for it using GR time dilation due to lower gravity and higher speed.
Right. We say time literally runs slower nearer the Earth in the stronger gravitational potential. GPT completely reframes this. It's not time that's warped.
It's the clock mechanism itself.
Kind of. It's signal phase compression caused by the graviton pressure.
Okay, give me the simple analogy here. Cut through the jargon.
All right, think of the graviton field near Earth as being like really compressed, like a thick gel or a dense fluid. Your atomic clock, the oscillator inside it, is sitting in this gel.
Okay.
The high pressure near the ground makes the oscillator sort of struggle. It experiences compressed phase intervals. It slows down its ticking rate.
Because it's pushing against more resistance.
Exactly. Now lift that clock up into orbit. The pressure is lower up there. The gel is thinner, more relaxed. The oscillator operates more freely, experiences phase relaxation, so it ticks faster.
So the effect we call time dilation is actually just the physical oscillator responding measurably to the local tension or pressure of the graviton field. The faster clock in orbit is just facing less resistance.
That's the proposed causal mechanism. And again, like with gravitational waves, it leads to a testable prediction.
Different from GR's prediction.
Potentially, yes. Because GPT ties the effect directly to the local pressure, PGR, it predicts tiny nonlinear variations in those timing corrections might exist. GR corrections are smooth, based mainly on altitude. GPT suggests you might see slight anomalies if a satellite passes over, say, a huge mountain range or a particularly dense bit of the Earth's mantle.
Because those would locally amplify the graviton field pressure.
That's the idea. A localized density change causing a localized pressure change, causing a tiny extra timing shift.
Wow, okay, that's fantastic. It takes this very abstract theoretical split and suggests a real-world, almost geological experiment.
Well, it has to be testable, right, if it's proposing a physical mechanism.
True. All right, let's shift back out to the cosmos. Light bending, gravitational lensing. We see these amazing images like the quadruply lensed quasar RxJ 1131-2231. GR models need complex dark matter maps to explain how the light bends to create those multiple images and their time delays.
Yeah, getting the lensing right often involves carefully distributing dark matter in the model. If you throw out space-time curvature, you obviously need another way to explain why light bends near massive objects.
So what's GPT's answer?
Simple refraction. Refractive bending through those graviton pressure gradients we keep talking about.
Like light bending through water or glass.
Exactly like that. Light passes through regions of higher graviton pressure and it gets refracted. There's a refractive index, NGR, which depends directly on the local pressure.
But wait, if it's just refraction, how does it perfectly mimic the bending angle predicted by GR's mass-based curvature? The observations match GR incredibly well.
But that's the connection. The refractive index, Angsting, depends on the pressure, PG. And the pressure itself is generated by the presence of mass. Mass structures the field, creating the pressure gradients.
I see.
So, while the mechanism is different refraction through a medium, not warped geometry, the amount of bending still traces back to the mass distribution that creates the pressure gradient. The effect looks the same, geometrically speaking, but the underlying cause is physical pressure.
Okay. And the time delays.
Yeah.
Where one image of the quasar arrives days before another.
Reinterpreted too. In GR, it's because the light travels a longer geometric path. In GPT, it's a phase shift, like running through thick mud versus running on pavement.
The path through the densest pressure gradient slows the light down more.
It slows the phase of the light more, yes. Its path of greatest resistance. And the sources claim GPT predicts these delays scale exponentially with the pressure gradient strength, not linearly like path length differences would suggest. Another subtle, testable difference.
Okay, largest scale now. The cosmic microwave background. The CMB. It's amazing uniformity across the entire sky. That's the horizon problem, right? How could regions that were never in causal contact end up at the exact same temperature?
Precisely. Standard cosmology's answer is inflation. This incredibly brief, unbelievably fast exponential expansion phase right at the beginning stretched tiny quantum fluctuations and smoothed everything out before the universe cooled and the CMB photons were released.
Inflation. It solves the problem, but it feels, well, contrived to some, needs exotic physics.
That's an extraordinary solution, yeah. GPT offers something, well, less explosive, more structural. It says the CMB uniformity comes from primordial graviton field coherence.
Meaning the field, the lattice, was already unified and structured from the very start.
That's the idea. The structured pressure field existed before photon decoupling. It acted as the underlying medium that naturally ensured thermal equilibrium everywhere, all at once. No need for a sudden, rapid smoothing phase. The inherent structure of the field provided the uniformity.
So it just eliminates the need for inflation entirely.
That's the claim. One mechanism field coherence replaces another, more complex one.
And the tiny temperature fluctuations we do see in the CMB, the anisotropies.
In GPT, those aren't quantum fluctuations blown up by inflation. They're just small, localized variations in the field coherence itself. Minor ripples or density differences in the primordial field. It feels perhaps more parsimonious.
Okay, let's bring this right back down to Earth one last time. A really simple local thing. A permanent magnet.
Like a fridge magnet.
Yeah. Why does it stay magnetic? Why does it keep its field going seemingly forever without any obvious energy going in? It seems simple, but explaining it perfectly within classical physics isn't trivial.
GPT offers a neat solution here. It says the graviton lattice has memory. A magnetic field is literally the torsional memory of that lattice.
Torsional memory, like a twist that stays locked in.
Exactly. A structural locked-in alignment of the graviton field within the magnetic material. It's not a dynamic effect that needs constant energy input. It's a persistent structural state of the field itself.
So when you heat a magnet up past its Curie point or, whack it with a hammer and it loses its magnetism.
You're not draining its energy. You're causing coherence loss. You're physically disrupting that locked-in alignment in the lattice structure. The memory gets scrambled.
That's elegant. It connects this huge cosmological theory right back to something you can hold in your hand. It suggests the field is a real, structured medium capable of holding these alignments.
It ties it all together, from the cosmic to the local.
Looking back across all 6 of these points, galaxies, waves, time, lensing, CMB, magnets, the core shift GPT proposes is fascinating, isn't it? It takes away the abstractions, the dark stuff, the curved geometry.
And replaces it all with varying levels of pressure and structural arrangement, coherence, within just one fundamental cosmic medium.
The universe defined not by invisible forces or abstract math, but by field organization, by pressure and pattern.
And the appeal is that it offers, or claims to offer, a single, unified framework. It's testable, it's causal, it provides mechanisms. It aims to connect everything from how galaxies form to fundamental forces through this one medium. The argument is, like you said earlier, more causality, less abstraction.
Which leads to a really potent final thought, something for you listening to chew on. If gravity, attraction, even the flow of time itself, if these are just local effects of graviton pressure and the coherence of this field, think about what that implies for future breakthroughs.
Yeah.
Right now, trying to manipulate gravity or time seems like science fiction, needing wormholes or vast energies.
But this theory suggests something different. Maybe the real breakthrough isn't about brute force energy, but about understanding and subtly manipulating these pressure fields, mapping them, distorting them locally.
If GPT's even partly right, maybe we don't need a bigger collider to probe gravity's secrets. Maybe we need incredibly precise measurements of those GPS timing variations near mountains.
Or experiments designed to induce localized coherence loss or amplify pressure gradients. It suggests the frontier might be in manipulating field coherence. That's a very different kind of physics. And maybe, just maybe, something we could start investigating right now.